Rotational inertia is very similar to inertia that we've talked about in the past. In the past, we said an object that has more mass had more inertia. And the things that we discussed were, if I have a biker on a bicycle, they have more mass or less mass, and therefore they have less inertia. Therefore, it is easier to get them going up to speed and making them come to a stop, versus a semi-truck that has more mass will have more inertia. It'll be more difficult to get a semi-truck up to speed or to make a semi-truck come to a stop. The same idea can be used in rotational terms. It's using Newton's first law. A spinning object will continue spinning at a constant angular speed unless acted on by a net torque. Just like linear motion, mass does matter. The greater the mass of the object, the more rotational inertia it will have. So the more massive objects will be more difficult to get spinning and more difficult to make them come to a stop from spinning. But there is a difference. The question could be, how do objects that have less mass have more rotational inertia? What is different about them? So for instance, if I have a hula hoop and I'm going to roll that down a hill versus a solid disc down the hill, solid disc has more mass, so it should have more inertia, we would think. But sometimes the hula hoop actually has more inertia. Why? Because it not only depends on the mass, but where the mass is distributed. And so objects aren't just more mass, more inertia. It's more mass at a greater distribution, more inertia. The greater the distance, the mass is from the axis of rotation, the more inertia the object will have. So if I have two objects, one hoop, one disc, and I start them both at the top of a hill, they are going to both roll down the hill, roll down the hill, roll down the hill, but the one with greater inertia will be the one that gets to the bottom last. So if they are exact same mass, here is my hoop where all of the mass is on the outside. Here is my disc where the mass is evenly distributed about all points. In the hoop case, every single particle of mass has to go all the way around the circumference. In the case of the disc, only the outside molecules have to go all the way around, where ones on the inside, they pretty much translate. They don't have to go in circles at all. They just spin in place as they roll down the hill. And every molecule in between has a different circumference, where in the hoop every single molecule has to go all the way around. That's going to give us more inertia, rotational inertia. We can actually calculate this. In the past, we only were able to say the greater the mass, the greater the inertia. Now, in rotational terms, we are able to calculate what is called the moment of inertia. It is the resistance of an object's change in rotation. And so the greater the moment of inertia, the more resistant to rotating the object is going to be. Also, the more resistant the object is going to be to stop rotating. Like I already said, the farther the mass of the object is, on average, from the center, the greater the moment of inertia it will have. So, in general, solid objects have lower rotational inertia than hollow objects, as long as they have the same mass. And if the object rotates about an axis that is not through their center of mass. For instance, if I have this hoop again, and instead of rolling it and having it rotate about a center point, I hold on to the top and I spin it like a top. Now it's rotating about a point along its vertical. That is a different type of rotation, and therefore will have a different type of inertia. But all types are going to be dependent on mass and mass distribution. Where is the mass located and how is that mass distributed? Here is the calculation. It comes from Newton's second law. You might remember from Newton's second law, F equals ma. That's not new. I can rearrange F equals ma to say the acceleration is force divided by mass. Then, another statement that is true is that torque is a force applied for a distance. The reason I'm using r in this case is just so that we have consistent variables throughout our problem, but it's just the distance from the center of rotation. I could use r, I could use d. It's the distance from where the object is rotating about, which really is the radius. Okay, so I rearrange that and I solve for force, which is torque over radius. Plug that in over here. And so now I have torque over radius divided by mass is my acceleration. At the beginning of chapter 7, we said a tangential acceleration is just an angular acceleration times radius. So what I can do is I can take my tangential acceleration out and put in my angular acceleration and radius. Now I have this kind of long, complicated equation. Angular acceleration times radius is equal to torque over radius over mass. When you rearrange, you get something that looks like this, where angular acceleration is torque over mr squared, and mr squared is the average value, oh, my pen isn't working, average value for moment of inertia. So mr squared, this should be mr squared, is the average value for moment of inertia of any object that is spinning. The greater the value of I, the more resistant to changes in spin or rotation that it has. So when we put this all together, we have mr squared is the average value, that is moment of inertia. Then I can take Newton's second law, F equals ma, and put it in rotational terms. The formatting didn't work out so well here. And the angular terms are, the similar term to force in rotation is torque. The similar term to mass in rotation is moment of inertia. The mass affects inertia in linear terms. The moment of inertia affects rotation in circular terms. And then instead of linear acceleration, angular acceleration. So here is Newton's second law, but in rotational terms. Now for units, I's units will always be kilograms, that's a K, times meters squared, because it's mass times radius squared. And then angular will be radians per second squared. But we drop the radians out, and so we get kilograms times meters squared per second squared, which is a Newton times meter. Okay, so the units work out just like the torque units we've been using in the past. So here is a practice problem. The moment of inertia of a 12.2 kilogram sphere of radius 0.623 meters when the axis of rotation is through its center. What is the moment of inertia? There's supposed to be a basketball going into the hoop here. And so a basketball is a hollow sphere. A hollow sphere has a moment of inertia, just like every other object has a moment of inertia, and the average is mr squared. But for a hollow sphere, we need 2/3 of mr squared. If you look at your formula sheet, you'll see that a solid sphere does not have the same moment of inertia. A solid sphere is 2/5 mr squared. So if I have a solid basket or a solid bowling ball, its moment of inertia is 2/5 mr squared. A little bit smaller. Like we said, some of the mass does not have to go through the entire rotation, where a basketball is hollow, and so all of the molecules have to go through the whole rotation when it's spinning. So to find the moment of inertia, I have the mass, and I have the radius. And so when I calculate 2/3 mr squared, I get 3.163 sig figs kilograms times meters squared. We can then follow that up with what is the torque needed to get this ball rotating at an angular velocity of 3 revolutions in 1 second if the ball started at rest and took 5 seconds to get up to speed. So again, the basketball is a hollow sphere, and I am looking for the torque needed. It still has a moment of inertia, and it's going to be accelerating. So I'm looking for torque. The moment of inertia we just found in the last problem, or I could write it in here again, but I know that that value is 3.16. The angular acceleration is dependent on the change in velocity that it experienced. So it's final angular speed minus initial angular speed over the time it took. Well, the initial angular speed was 0. It started from rest. And the time it took was 5 seconds to get up to speed. The final angular speed, it says 3 revolutions in 1 second is the speed it got up to. Well, 3 revolutions is 3 times 2 pi. And it was rotating that in 1 second. So it's going 6 pi per second. So for my angular speed, I can take 6 pi for the final speed, 0 for the initial in 5 seconds. If I calculate that out, it's 18.84. Or I can just plug this whole equation into my equation here. So this is 18.84. 84. And so when I calculate here, I get 11.9 newtons times meters. That is the amount of torque it would take to get the ball spinning at 3 revolutions a second in 5 seconds.